Hi everyone, welcome back to UMEED NEET English batch. Friends, as you know, in this batch, we are going to cover each and every topic for NEET, each and every chapter for NEET along with their numericals. And we are going to prepare those topics along with numericals for NEET 2025. The best part is this batch is absolutely free. You can watch it on YouTube channel and you can also watch it on PW app if you want to download these notes as well, right? So friends, in the last class we completed, I think, motion in a plane. Before that we completed motion in 1D. We completed relative motion also in the last class. So basically we have completed kinematics. Now we are going to start dynamics, right? So if you remember, when we started kinematics, I told you that we have started mechanics and we have started one part of mechanics in which we are going to only talk about characteristics of motion. We are going to talk about distance, displacement, acceleration and each and everything, but we are not going to talk about what has caused all of these things, right? What has caused the body to move or to accelerate or to stop if it was moving initially. We are not going to talk about the cause. We are not also going to talk about the mass of an object when we are dealing anything under kinematics, right? But today we are going to start Newton laws of motion, and I know that you are pretty aware of this concept, of pretty aware of this fact that this is one of the most important chapters, because in this chapter you are going to basically learn all the things about free body diagrams. You are going to talk about equilibrium, you are going to talk about pulley block systems, and those questions are going to come in different chapters also, right? So this is going to be very important. So please do attend this class right from start till the end, right, to gain the maximum benefits. And what are going to be the today's topics? So today we are going to talk about some of these topics. Definitely we are going to start with the definition of force. Then we are going to talk about first law and second law of motion. Then when I'm going to actually break the class into something like, we are going to first talk about normal force, we are going to talk about tension, then we are going to talk about pulley block system. So these are those forces which we usually encounter in different questions, right? So first we are going to discuss these forces exclusively. Then we are going to talk about spring force, pseudo force and friction, and in between of those we are going to talk about almost every other topic which comes under Newton laws of motion, right? So let's start. Let's not waste any more time. Let's start our class. As I've told you, first let's quickly try to write what do we really mean by force, right? So I mean, right from the junior classes you might have learned this, that force is something. Okay, just a second. Force is actually an effort in form of push or pull. So a very easy definition: it's an effort in the form of push or pull which may do what? Which may bring change in, which may change state of body. That means it can make a body accelerate, deaccelerate, right? It can actually, if a body is moving, it can stop that body. If a body is at rest, it can bring that body into motion. It can change the direction of motion. Change the direction of motion. What else? It can change the shape or size. So this is pretty basic definition of force. You might have learned this definition, right, starting from grade 8, right? Usually in grade 8 we only call it as push or pull. Then these are some of the added part to this definition that we usually learned in grade 9th or 11th. So we are pretty you might be pretty comfortable with all of these things. What I really want you to focus on is that this thing, that push or pull. So whenever we are going to talk about different forces, we are going to actually try to define what type of a force it is, right? So if we are talking about normal force, tension, we are going to discuss those separately, but we are going to define them whether it is a pushing force or it is a pulling force, or a force might can do both things, right? So we are going to do that as well. Then some of the basic things, of course, it's a vector quantity. SI unit is Newton, right? Or kg meter per second square. Or if you want to convert it into CGS unit is going to be dyne or gram centimeter per second square, right? You can also do the conversion. These are some of the basic things about the force. Now, in our universe, mainly there are 4 types of fundamental forces, right? So there are only 4 fundamental forces as of now. So which means whether we are going to talk about normal force, whether we are going to talk about tension, whether we are going to talk about any type of another force, all of those force eventually comes down under one of these 4 forces, right? They come out under these categories, and these are I'm going to write it in order of their strength. So these are strong nuclear force, then we have got weak nuclear force, then we have got electromagnetic force, and the last one is gravitational force. So indeed, gravitational force is actually the weakest of all of them. It's quite a weak force. In this chapter, we are not going to talk about strong nuclear force or weak nuclear force. We are going to talk about those things in under modern physics. We are going to almost all of contact force. I should not say almost. All of those contact forces that we are going to talk about in this class will come under electromagnetic force, right? So this is very, very important. So electromagnetic force basically means we are going to talk about again from the junior classes you have learned this: like charges repel, unlike charges attract, right? Like poles of the magnet repel, unlike poles of the magnet attract. That means when we are talking about magnets or moving charges, we talk about magnetic force, moving charges in a magnetic field. Or when we talk about stationary charges, we talk about electrostatics force or Coulomb's force. All of those forces comes under electromagnetic force. So this is very, very important whether we are going to talk about any sorts of force, because what's going to happen is we are going to now talk something about contact force, right? So contact force basically means, let's suppose that you have got one body over here and you have got another body over here, something like this, and you are applying a force on this body. Now in between of these, they are in contact with each other, so they will apply a force on each other. We are going to define that force. You know that force is also a normal force, but we are going to talk about all of those things. But the first thing that I want you to know is, if two bodies are if there is a force which is a contact force, then it will come under electromagnetic force. That is for sure, right? So now after all of these things, after discussing electromagnetic force, gravitational force, electromagnetic and all of these things, now let's move to laws of motion, and then after completing laws of motion, we'll come to the different forces like tension, normal and all of those things, right? So now again, Newton laws of motion, you know that every body will be at rest or in its initial state of motion unless and until an external unbalanced force acts on it. It is also known as law of inertia. So nothing to worry about over here, right? Every body continues to stay at rest or uniform motion in a straight line until and unless an external force is there to change that state, right? So this is very, very important. This is nothing but this is your law of inertia, right? And when we are going to talk about inertia, we are going to also say that inertia is basically a property of mass. So greater the mass of a body is, greater is going to be the inertia of the body, right? Then we have got like different sorts of inertia: inertia of motion, inertia of direction, and inertia of rest. But generally, I mean, question does not comes from here, so you don't have to worry about all of these things, right? The first law is quite simple: unless and until an net external force acts on it. So this is very important. A net external force must act on the body. If this is 0, then we are going to say that there will be no change in the motion of the body. No change in the motion of the body, right? So that's it. It was just a formality for us to complete it. We really didn't had any problem. I mean, surely you also didn't had any problem in Newton's first law of motion, right? We need to actually keep one thing in mind, that all of the laws of motion like Newton law, first law, second law and third law, these are applicable to a certain conditions. This is very important, right? So obviously learning Newton laws of motion, understanding Newton laws of motion is not a big deal, but to understand when we can apply a Newton laws of motion, when we cannot apply, and when we cannot apply Newton laws of motion, what we can modify, right? What we can do to that particular situation so that we can apply. So these are some of the important things that we need to understand, and for that I have got different notes for you. So first of all, Newton's laws of motion are only valid for a set frame of reference. Now you know that what do you really mean by frame of reference, right? And these frame of references are known as inertial frame of reference. These are known as inertial frame of reference. It means that these frame of reference have either acceleration 0, right? Or I mean, if they have got acceleration 0, then we can have both the cases, like they can move with, they can be at rest. So these frame of reference can be at rest, or they can move with constant velocity. So this is what I was talking about. We are going to start everything from the basics, but we are going to actually emphasize more on the most important topics. So this is one of the most important things, and sometimes I have seen that students actually, they really don't care about all of these points and they move on. And when things like pseudo force comes, or when things like circular motion comes, they face serious problem drawing free body diagrams, applying second law of motion. So this is very important. Please understand that Newton's laws of motion is valid only for inertial frame of reference. What do you mean by inertial frame of reference? That means they are not going to accelerate. So acceleration is definitely going to be 0. Either they can be at rest or they can move with constant velocity. That's completely fine with us. Now if they are accelerating, if we have got an accelerating frame of reference, right? If we have got a non-inertial frame of reference, then what are we going to do? We are going to talk about it in today's class only, but some time after. The next point is that Earth is also an inertial frame. It is we take it as an inertial frame of reference, but strictly speaking, Earth is not inertial. We all know that Earth is moving with it has got acceleration. Of course, it is spinning around its axis, and it is spinning around a common center of mass of solar system, that is Sun, right? Somewhere near Sun. So all frames moving uniformly with respect to an inertial frame are themselves inertial. Pretty simple. It means that if, let's suppose, A is a frame of reference, it is an inertial frame, and we have got another frame of references which are moving with constant velocity with respect to the former frame of reference, then we are going to say that okay, all of those frame of references are also inertial frame of reference, right? We take all frames at rest or moving uniformly with respect to Earth as inertial frames. This should be also be really fine. That means on Earth, if you are going to take multiple frame of references and they are at rest or they are moving with constant velocity, they are going to be the inertial frames. This is very important, right? Now the thing is, after learning Newton's first law of motion, let's quickly jump to something that is called as momentum. A very easy thing. Momentum is nothing but it is the quantity of motion, right? The total quantity of motion possessed by the moving body is known as momentum of the body. It is the product of mass and velocity. All right, let me draw it vectorly. That will be, I think, a good idea. So let's suppose we have got a body and I am drawing a body on a Cartesian plane. So I've got a body somewhere over here and it has got velocity v. Let's say it has got velocity v in this direction. And it has got mass m. Right? So what we are going to do now is we are going to say that okay, let's say we have to write momentum. We are going to write something like momentum equals to mass times velocity. Now please remember this diagram, because when you are going to talk about angular momentum, we are going to use this diagram and we are going to just say that okay, if you want to find out the angular momentum, you can easily find out the angular momentum using this position vector. Right now we don't have to draw the position vector, but you can use the same diagram over there as well, right? So this is very important. Momentum is equals to mass times velocity. SI unit is going to be, of course, kg meter per second, right? Other than that, it's a vector quantity, nothing to worry about. Then comes Newton's second law of motions. Newton's second law of motion states that force acting on a body, net force, and of course we are talking about net force acting on a body, is directly proportional to the rate of change of linear momentum, that is dp by dt. This is what Newton's second law states, right? So removing the proportionality sign, the proportionality constant comes out to be 1. This is nothing but this is dp by dt. Let's write it in vector form. Now we know that momentum can be written as mass times velocity. So if that is the case, quickly see, we are moving quickly from all of these concept topics, because the main part is remains in quotients, right? In quotient solving, we are going to do that. So if momentum is mass times velocity, what we can write over here is force can be written as d mv by dt. Is that correct, right? So this is going to be a new formula. Now two things can happen. Mostly what we are going to do is we are going to actually apply what we can say, apply product rule over here. So if I'm going to apply product rule over here, I'm going to write v dm by dt plus m dv by dt. Hopefully everything is clear with this thing. This is a general form, right? Now the thing is, obviously most of the time what's going to happen is that dm by dt is going to be 0. Why? Because let's say mass is constant. You are going to say, sir, obviously mass will remain constant. There are cases when mass is not constant, right? Like for example, as rocket propulsion. So when we are going to talk about rocket propulsion, mass is not going to be talking. Now here we are talking about the mass of all of those propellant gases and the liquid fuel, right? So if mass is constant, definitely dm by dt will be 0. So in that case, you will get Newton's second law of motion in the way in which you have seen it. So in that case, force will be actually equals to mass times dv by dt, and that is acceleration. And by the way, I've started all of these things with writing that this is nothing but this is the net force, right? So this is one of the case. The second case is going to be when velocity is constant but mass is actually changing, right? So if velocity is constant, and this is for example, this is for rocket propulsion. Now in this case, obviously we are going to write this will become 0. That will, the force is going to be v, and I'm going to write it as v relative dm by dt. Now what is this v relative? This is the velocity of the ejected gases with respect to the rocket, right? So this is the case for the rocket propulsion. Now this is very important if you want to write down anything for the rocket. I'll quickly explain something over here. Let's suppose that we have got a rocket and it is moving with, let's say it is moving with constant velocity, right? Its velocity is constant. So if its velocity is constant, the net force on it must be 0. So one of the force which is acting on it is definitely mg. So in this particular case, I'm just drawing an example for you. For this particular case, I'm going to write something like this is my force. So v relative dm by dt will be equals to mg. For this particular case, if it is accelerating, then the net force or the net acceleration can be found out subtracting these two. So with this, I think we can move on to some new topics. We are going to obviously use Newton's second law of motion almost everywhere, right? Now again, we have got some important points over here. One of the important point is that force cannot change the momentum along a direction normal to it. It is quite important and easy to understand as well, right? So please remember this point, that if you have got a force along a perpendicular direction to a velocity, then that particular velocity will not change, right? It is quite easy to understand. I'll give you an example, and I'll give you an example of circular motion. I mean, when we talk about centripetal force, although we have not completed circular motion yet, but I can assume that you know all of these things. This is centripetal force. The only job is to actually change the direction of the body, right? It cannot really do anything with this component, right? Now the thing is, Newton's second law is strictly applicable to a single point particle. This is also important. It is only for a single point particle. In case of a rigid bodies or system of particles or system of rigid bodies, F refers to a total force acting on system and refers to acceleration of center of mass of the system. Again, we are going to deal with center of mass after 1 or 2 chapters. But still, this point is important for you to understand. The internal forces, if any, in the system are not to be included in F. We are not going to talk about in internal forces. That when we write F equals to MA, that F is net forces of all the external forces, right? This is also very important. I'm going to give you one more example of the above example. In collisions also, we are going to use that the force can't change the momentum along the direction normal to it, right? That is also important. Acceleration of a particle at any instant and at a particular location is determined by the net force acting on the particle at the same instant and at the same location, and is not in any way depending on the history of the motion. Very important thing. I mean, no matter where the particle has come to that place, we don't have to worry about all of those things, right? Easy things. Now let's come back to something which is known as normal force, right? Shall we start normal force? Now I have already told you, when we are going to talk about forces, first let's define the forces in terms of like the definition. What do you really mean by a normal force? So we are going to define normal force something like, we have got let's say this is a ground, and we have got a body of mass m, right? Gravitational force acts on the body. It pulls the body down with the force of mg, right? And then we have got two surfaces over here which are in contact with each other, right? We have got two surfaces, surface of the block and surface of the ground, right? The ground actually tries to push back the body in perpendicular to the direction, something like this, and this force is actually known as a normal force. So normal force, first thing, normal force is actually a pushing force. It is a pushing force which acts perpendicular to the surface, right? Is that correct? Which acts perpendicular to the surface when surfaces are we can write pressed, when surfaces are pressed, right? So let me give you some quick examples over here. Let's suppose we have got an inclined plane and we have got a block, something like this, right? And the mass of the block is m, this is theta. Now we all know how to quickly draw all of these forces. This is mg. I'm going to draw it from here. This is mg, right? So this is, if this is mg, this is going to be 90 minus theta, of course. This is theta, this is going to be 90. So this is going to be mg sine theta, right? This is going to be mg sine theta. So one of the component along the along perpendicular to the inclined surface is going to be mg cos theta. So with this force, the gravity is actually trying to push the block into the inclined plane, right? Into this surface. So the normal reaction will be drawn something like this, and under equilibrium, this normal reaction will be equals to mg cos theta. Is that correct? Right? If you have got a spherical surface, then the normal force will pass through this point, the point which is touching the ground, and that will be equals to the weight of this sphere, right? Another example, let's say we have got two blocks, something like this, kept like this, right? Draw the free body diagram for all of for this system. Draw the free body diagram. I'll tell you, I've got M1. Pause the video, draw it by yourself. M1, M2, all the surfaces are smooth. Draw a free body diagram. Obviously, you're going to draw it something like this. You're going to say, okay, fine. There's M1G, there's M2G. Right? There's normal N1, there's normal N2, and then there's going to be a normal something like this, and there's going to be a normal something like this. Is that so? No, that's not correct, right? We are not going to draw these normal between. I mean, if they're in contact with each other, I don't have any problem. I mean, when I say I don't have any problem, I don't have to draw the normal forces. Please remember, we are going to draw the normal forces only when the surfaces are being pressed by anything, right? If they are in contact with each other, normal force will not come in place, right? Why normal force was coming over here? Because of this Ng, right? This Ng was actually pressing the two surfaces. So the thing is, over here we don't have any normal forces till now, but if I'm going to draw a force something like this, let's say I've got a force, an external force F acting over here. Now definitely on M1 a normal force will be drawn something like this, right? And on M2 normal force will be drawn something like this, and obviously they are going to be equal in magnitude and opposite in direction, right? So that is absolutely correct. So this is important, how to draw normal forces. Normal forces are always going to be perpendicular to the surfaces. Now after this, we can also define normal force as that it is the component of the contact force. After we are going to complete friction force, we are going to talk about contact force, right? So when we are going to talk about contact force, now contact force will have two components, and the perpendicular component, the vertical component, will be actually called as the normal force, and the tangential component will be known as the friction. So this is actually really important. So I mean, it will be good for your concept that you remember this definition, right? I have written it over here as well. It measures how strongly the surfaces are in contact, are pressed against each other. So if you are not pressing two surfaces, we are not going to talk about normal forces. Normal force acts in such a fashion that it tries to compress the body. Normal is dependent force. It comes in role when one surface presses the another surface, right? So hopefully everything is clear. For more clarity, let's solve one or two more problems on this. Let's suppose that we have to draw a free body diagram over here, right? So if we have to draw a free body diagram, let's draw it for first 10 kg. So we have got a 10 kg block. Obviously I can see that I've got an 100 Newton over here. So because of this 100 Newton is going to press the another block, and that block is going to apply a normal reaction. I'm going to write it as N, right? Then I've got 100 Newton over here as well, which is the weight of this block, and then I've got N1 over here, right, which will be actually equals to 100 under equilibrium. Now I have actually at multiple places, just because I'll not write this N because it stands for Newton, right, to avoid confusion. Just because I have used multiple times equilibrium, let me explain what equilibrium means, right? Anyway, we are going to talk about it later. So equilibrium basically means, in physics, it's mainly of two types. One is translational equilibrium and rotational equilibrium. Also sometimes we define it as static and dynamic, but right now we are going to only talk about two things. One is that if we are saying that a system is in equilibrium, a system can be comprised of many particles which is inside of it, right? Like for example, is if I am calling this as a system, what do I am calling it? Obviously there will be no change in the grounds, right, these surfaces. So the system comprises of this 10 kg block and this 20 kg block and all the external forces, right? So when I say I have got a system, now I am not going to change anything into it on my own. Now if this system is in equilibrium, then the net force acting on this system will be 0. And when I say net force acting on this system, basically net force on this will be 0, net force on this will be 0. And when I say net force will be 0, I necessarily does not mean that the body will be at rest. I just mean if net force is 0, go back to Newton's first law. This is the thing, Newton's first law was very easy, but can you quickly relate every question to Newton's first law? That's important, right? So please don't just assume that, okay, if net force is 0, the body will always be at rest. Obviously, here the body will be at rest because we can see that the scenario is something like this. So we have drawn everything for the 10 kg block. Now let's draw for the 20 kg block. So for 20 kg, I've got 200 Newton. I've got normal reaction over here applied by the 10 kg surface on this, right? Then I've got another normal reaction which is actually N2. I'm going to write it. Then I've got 50 Newton, right? I've got 50 Newton over here. So if this is 50 Newton, this is going to be, this is 50 cos 30. And I've got another force over here, that is 50 sin 30. Is that correct? Right? So after this, you can draw all of other things. Now N2 will be actually equals to 200 plus 50 cos 30. Right? That is how you are going to draw all the normal reactions and all the forces over here. Now I've got another question for you. Do it by yourself. This is the question. Find the contact force between the 3 kg and 2 kg block. Take, pause the video, solve it by yourself, then I'll explain. Alright, so hopefully you have done it. So for these kinds of problem, it is quite easy. Just write down the net force. The net force is going to be the net force that will act is 100 minus 25, that is 75 Newton in this direction, right? And after this, use the Newton's second law. Using Newton's second law, we can actually write down the acceleration of this system, right? So acceleration of this system will be the total force divided by the total mass. So total mass is 3 plus 2 kgs. So that's going to be 75 over 5, that is 15. So 15 meter per second square is the acceleration, right? Now after this, draw the individual diagrams over here, individual blocks over here. So I've got 3 kg and I've got 2 kg. So for 3 kg, I know one thing for sure, that it is moving with 15 meter per second square of acceleration. And so is this 2 kg block. What else I know? I don't have to draw the weight and the normal reaction by these by the surface of the ground, right? All I have to do is, I know that I have got 100 Newton over here, and I'll draw a normal reaction something like this, and let's say I am calling it as N, and the another normal reaction on this 2 kg will be also N. Now please understand, I've got no other force on this 2 kg, right? But I know that it is moving with 15 meter per second square. So now again, let's apply the Newton's second law over here. So Newton's second law is going to be N equals to 15 times 2, of course, which is 30 Newton. So I've got what my normal reaction is. And if you're going to actually again apply 100 minus 30, again it's going to be 75, and 75 divided by 3 is again it's going to be 15. So the correct answer is actually, let's quickly again understand if we have got any other problem over here. Quick. I think we have done everything correct. Let me check the options. Yeah, we have done one mistake. I have got also this 25 Newton over here. I have forgot it. So let's also mark this 25. This is also I have got. So now the thing is, I'll write something like n minus 25 equals to 15 times 2. So n will be equals to 30. So that will be 55 Newton. Now let's check. So 55 Newton is coming our normal force. Over here 100 minus n equals to 3 times 15, that is 45, and n will again come out to be 55 Newton. So this is the answer, right? So my bad, I forgot that we have got one more force over here of 25 Newton. Now after this, I have got one more question for you for homework. So do this, give your answer in the comment section. This is slide number 13. So this is your homework. Do write your answer in the comment section. All right. So this is for your practice. Similar thing you have to do. This is 50 Newton, that is 30 Newton. That means net force is in this direction, which is of 20 Newton. 2 plus 5, 7, 10. 20 divided by 10, that is 2 meter per second square. The system is moving 2 meter per second square in this direction. So now draw the draw a free body diagram for this one and free body diagram for this one and this one, right? Using 2 kg and 3 kg, you can find out the normal forces between AB and BC. After that, that's all you need to do. So they are going to be two pair of normal forces, one between A and B and one between B and C, right? Sorry. All right. So now let's move to another topic, which is tension. So I have told you we are going to complete each and every forces, something like this. Then we are going to talk about some more problems. Now when we are going to talk about tension, first of all, tension always acts along the string and in such a direction that it tries to reduce the length of the string, right? First, let me explain you what we are talking about. Let's suppose we have got a rope. We have got a rope, something like this. And let me attach this rope, let me suspend this rope from a rigid support, something like this. So I've got a rope over here, right? At this particular end, let's say I have tied a mass M. So now what's going to happen is that gravity will always pull this mass down with a force of mg, right? And because of this force, this particle, because the endmost particle is attached with the block also, right? This particle will also feel that force mg, and because we have got infinite many adjacent particles, like I've got one particle over here, I've got another particle over here, I've got another particle over here, I've got another particle over here, and every other particle is holding their adjacent particles with intermolecular force, right? So because of this, there will be a force, we are going to say force produced in the string. That force is known as tension, right? That force is actually known as a tension. So to define tension, we are going to define it something like this, that tension is actually a pulling force which comes into existence because of, as a consequence of electromagnetic force, right? It's a direct consequence of an electromagnetic force. Now the thing is, first thing we have done that it is a pulling force. Second, it will never push an object, right? So if I've got no block over here, I've got nothing over here, it will be a slack thing. You can imagine it something like this. Let's suppose I've got a ground over here, and I've got a rope something like this, right? And I've got a block over here. Let's suppose this is a rope. right? The rope will not be able to withstand the weight of this block, and it will actually collapse. It will slack. It will slack, and block will actually fall under free fall, under the influence of only gravity. That's it, nothing else. This is very important to understand, right? Yes, I mean, if there was a rod, a rod can actually also push something. So we have got a difference between a rod and a rope. Tension can act along a rod as well, right? So one important thing, tension is a pulling force. It can always pull, it cannot push any object. The another important thing is how to draw tension. How to draw tension forces. So to draw tension forces, first let me explain that these things are known as contact points. These things are known as contact points. So I've got one contact point over here. I've got another contact point over here. Now this is actually really important. Why? Because again, when you are going to actually apply Newton's second law of motion, you must be able to first draw the direction of forces correctly. Else what will happen is you will instead of adding tension, you will subtract it. So when you have got contact points, always the tension will act something like this. Over here, the tension will act opposite to the direction of opposite to the contact point, something like this. Over here, the tension will act something like this. In other words, tension always tries to reduce the length of the string, right? So that's also how you can actually understand it. Tension always tries to reduce the length of the string. Next example, let's suppose we have got a system like this. We have got blocks over here. Okay. And I've got a rope, and I'm applying a force on this rope. Let's say in this direction, right? And this force is, let's suppose it is directly connected with M1, directly being applied to M1 and M2, and I've got a rope over here, right? And this is how the condition is. Now the thing is, there are some assumptions that we usually use in our questions. One is that usually our ropes are massless and inextensible. Now this is very important to understand, because when we are stating that our ropes are massless, what do we really mean by this is that tension will remain same all along the rope. Tension is constant along rope, along length. It means that if I have got one rope, tension will remain same all along it. Please remember it, very important concept, very basic concept, and you are going to actually solve almost every other question which will come in NEET, which from pulley block or anything like this, if you remember all of these simple concepts, right? So if a rope is said to be massless, it means that the tension will be constant all along the length of the rope, and it makes complete sense, because please see, if you are going to ask me that, okay sir, fine, what about this point of contact? I've got like many particles now. So what about this point? And what about this point? There is a difference between this point, and this point. Well, if you are saying that the rope has got some mass, then this point has to actually take the weight of this entire rope and the block, right? But if you are going to talk about this point only has to hold this mg. right? So the tension will be different if you are not going to assume that the rope is massless. So our ropes are usually, they are going to be massless, and when we say that they are inextensible, that means their length does not changes. Their length is constant, which means all the particles they move, they move with same velocity. Now again, this is very important. I'll tell you why. So if this, because of this force, this block is, let's suppose it is moving with 10 meter per second of velocity and with certain acceleration for that matter, then this rope will also move with that 10 meter per second. This M2 will also move with 10 meter per second. There is no two way about it. Because if they are not moving with same velocity, that means that they are not inextensible. That means there is some extension which happens in springs, right? Spring, if you have got two ends connected to a spring, two blocks connected to a spring, one can move for a certain period of time, another can be at rest. So this is what we mean by inextensible. And this is also means that if two points of a rigid rope is not moving with, are not moving with same velocity, it means that they are broken, right? So we don't want that. So to draw the tension over here how we are going to do it? So if you want to talk about M1, for M1, this is force F, we have drawn it. This is the point of contact that you want to look for. So this is how you are going to draw tension T on M1. Right? So for M1, if you want to write down the second equation, if you want to write down the second law, you're going to write F minus T equals to M1 into A. Of course, F minus T, because the system is moving in this direction. If you want to write down for M2, you're going to write down the tension something like this. Why? Because this is the point of contact. We are going to draw it tension something like this. And we are going to write tension equals to M2 into A. That's it. Obviously, all the surfaces are assumed to be smooth here. Right? Now the thing is, after learning all of these things about tension, I think now we can move to some concepts, like for example as bodies hanging vertically. I'll give you some examples. Let's suppose again we have got a rigid support over here, a wall, and then I've got a rope, something like this. Let's say I've got like 3 blocks. 3 blocks are going to be sufficient to explain. Let's say this is M1, this is M2, this is M3. Let's draw all the forces over here. Let's draw it on M3. I'm talking about M3. So on M3, I've got M3G. I've got, let me write it as T3. Because I've got 3 ropes, I have written T3, right? Over M2, I'll write 1 force T3 plus M2G. Is that correct? Why I've written it as T3? Because first same rope, and this is a point of contact, so opposite to the point of contact T3 plus weight of M2G, right? Weight of M2, which is M2G. On M2's upper point, I've got, let me write it as T2. Over here, I'm going to write again T2 plus M1G, and over here I'm going to write T1, and over here I'm going to write T1. So you are going to ask me, why have you written 2 times of T1 over here? So this T1 is the force applied by the rope. It is actually pulling the system in upward direction. And this is the force applied on the support by the rope. It is pulling it down, right? So, I mean, you can start with over here, you can say that, okay, sir, for this T3 will be actually equals to, because over here, this is in equilibrium. So, for M3, if it is in equilibrium, net force must be 0. So, T3 must be equals to M3G. So, now you can substitute T3 over here. So, that means T2 will be equals to T3 plus M2G. So, T2 will be equals to M2G plus M3G. Now I think you got the drill. So that means T1 will be, I mean, obviously this is just to show you how to write, how to draw tension forces. It is not for, it is not to say that you have to do it something like this. Obviously, when you are going to see a diagram like this, the T1 will be directly written as total mass multiplied by gravity. That's it. You don't have to worry about anything, right? So hopefully everything is clear till here. Now after this, they were hanging vertically, there was no big difference. Now what happens, sometimes they accelerate this whole system, right? They do accelerate it. So if they do accelerate it, just if let's say that it is accelerating in upward direction, the whole system is, this is another case. If they are saying that the whole system is accelerating in upward direction with an acceleration A, right? Now write down the equations. So now for this M3C, you have got T3 and you have got M3G. Now don't equate them. Why? Because it is accelerating, right? And it is accelerating in upward direction. So I'm going to write T3 minus M3G equals to M3 into A, right? For M2, you are going to write T2 minus T3, or obviously for you have got T3 plus M2G equals to M2 into A. You can write the equation something like this if the system is accelerating, right? Hopefully everything is clear. Now let's come to a pulley block systems, and for pulley block system, again I'm going to tell you the same things. Hopefully you can see the diagram clearly. In the arrangement shown in the figure, find the ratio of tensions in the string attached with the block and with the 1 kg. Before moving to this thing, let me explain something about the pulley block system. For the pulley block system, what happens over here is, let's suppose that we have got a support over here, and on this support I have got a pulley attached. What does pulley do? A pulley is actually a type of a simple machine which actually changes the direction of force, right? So I've got a single rope attached to this pulley, something like this. So again, let's find out the contact points. I've got one contact point over here, I've got another contact point over here, right? Then I've got two blocks. Let's start with the two block system. I've got one block over here, I've got another block over here. This pulley is, again, it is massless and frictionless. If there will be friction, then tension will not be same, right? So because of friction, tension is same along a single rope or along a same rope. An important concept, right? So if you want to draw, again, if you want to draw the forces over here, let's say this is M1, this is M2. For this example, let's say M2 is greater than M1. So they are moving with an acceleration A. I've got M2G over here. I've got tension over here. Now you must be really quick to write the directions of tension. So this is how we are going to write tension. Same rope, same tension. Over here, if you want, you can draw tension something like this. So on the pulley, you know that the net force is actually acting as 2T, which you can again write something like this. On the support, the reaction force is actually is going to be 2T, right? So if you want to write down the equations, I can write down the equation. We can rewrite for the M1 as, obviously you have got M1G also. So you have got T minus M1G equals to M1 into A, and M2G minus T equals to M2 into A, right? M2G minus T, and we are writing it something like this. It is moving with an acceleration A in upward direction. That's why we have written T as a greater force, right? So if you're going to add them, you can find out what acceleration is. Is that correct, right? So let's add them. So adding them will give M2G minus M1G divided by M1 plus M2. And from now on, you can quickly rewrite this thing as, this is nothing but this is net force divided by the total mass. That's it, right? Also, if you'll again substitute acceleration over here, you can find out what tension will be. Tension will come out to be something like 2 times of M1 M2 G divided by M1 plus M2. So having said that, let's now solve one or two problems for this. Let's suppose we have got question something like this. In the arrangement shown, find the ratio of tensions in the strings attached with 4 kg and 1 kg block. All right. So the thing is, it is actually quite simple. I'll suggest you to do it with both the ways. Quickly do it using the concepts of net force, right? Also, one more thing, if you have got a single rope, here's a tension T. So I'm going to write T over here as well, because it's a same rope, right? For this one, it is actually 10 Newton. And over here we are going to draw, let's say I'm going to draw T dash. So draw the free body diagram by yourself, quickly solve, pause the video and then I'll solve it. So now friends, as you can see that we have got the net forces over here is going to be 0. If you want to find out the acceleration is going to be 0, because we have got 40 Newton over here, we have got 40 Newton over here, right? So if the acceleration is 0, this tension will be exactly equals to 40 Newton, right? And over here, this tension will be equals to 30 Newton. And again, this will be 40 Newton, right? So the ratio is going to be 40 divided by 10, that is 4:1, that is option B. Moving on to the next one, let's find out this one. Again, pause the video, solve it by yourself, then check your answer. Let's do it quickly. Now over here again, let's find out the tension. So the acceleration will be net force 40 plus 60 is 100, 100 minus 20, 100 minus 20 is 80 divided by 12. Is that correct, right? Hopefully everything is clear till here. So this will be 40 by 6 and 30, 20 by 3. So 20 by 3 meter per second square is the acceleration that we are getting. And now we can actually find out the tension. So I can find it over here. So T1 minus 20 equals to 2 into 20 by 3. So T1 will be actually equals to 40 by 3 plus 20. So this is going to be 60, so this is going to be 100 by 3 Newton. Please check. So T1 is getting out to be 100 by 3, and after this T2, for finding out T2, what we are going to do is we are going to actually write 60 minus T2 equals to 6 into A is 20 by 3. So T2 is actually the T2 is actually coming out to be 20. Let's 20 is 60 by 3, right? So C option is correct. Hopefully you have got it. Now let me give you one or two questions in homework, right? Like this one. Now using concepts, using questions like this, we are going to also learn about the concepts of constrained motion. Constrained motion is something which is not entirely in NEET. It's definitely it comes in JEE, but it does not comes in NEET. But we can actually understand it pretty easily from this concept. What does constrained motion basically means? It means that, okay, if this block is connected with this block and this block is moving with an acceleration a, this block will also move with an acceleration a. If this block has some velocity v, this block also will have certain will also have the same velocity v, right? Now the thing is, after this we have got let's quickly write down the forces. We have got 40 Newton over here. So I've got only one force because there is no friction or any force over here. So the net force is 40 Newton divided by the total mass is actually 6 kg, right? So that means the acceleration is going to be 20 by 3 meter per second square. So we have found out what acceleration is, 20 by 3, quite easy. Now same acceleration is going to be for this one as well. So tension equals to 2 times of 20 by 3, that is 40 by 3. 40 by 3 Newton, 40 by 3 and 20 by 3, that means option A is correct, right? Moving on to the next one, and we have got some question something like this as well, right? So in these types of questions, what we need to do, we have got in the adjacent figures masses A, B and C are 1 kg, 3 kg and 2 kg. All right, so this is 1, this is 3 and this is 2. This is 1 kg, this is 3 kg and this is 2 kg. Find the acceleration of the system and tension in the strings, right? So now what we can do first is, let's quickly write down, this is going to be, we write it as ng sine theta, right? So we are going to write 2g sine 30. We are going to write a tension over here. So let me write it as T1. So same tension will act over here as well. I'm going to write it as T1 also, right? Then for B, I'm going to actually draw two forces. So for B, one of the forces will be drawn something like this, and that will be 3g sine 60 and a tension something like this. Let me write it as T2. On A, same tension will be act something like this, same T2, and on this side this will be 1g sine 60. So I have drawn all the forces which we need in this diagram. Now if you want to find out the acceleration, all you need to do is you need to write down the formula, write down the net force. Net force is, my dear friends, g sine 60 plus 3g sine 60 minus 2g sine 30 divided by total mass, that is 6 kg. And after that you can again write down the equations for tension as well, right? As quickly you find out the acceleration. After that, just I'll write it for once. We'll write something like T1 minus 2g sine 30 equals to 2 into A. That's it. Right. So with this, now let's move to the another topic, that is spring force. So till now we have completed normal, we have completed tension, and now let's talk about the spring force. Now, similar to tension, spring force can also pull, but unlike tension, spring force can actually push as well, right? So if let's suppose we have got a wall over here and we have attached a rope, we have attached a spring something like this, and let's say this is right now in its natural length. Natural length basically means that there is neither extension nor there is any compression, right? At this point, if we are going to actually now apply an external force to this end, the spring will start to elongate, right? And as soon as the spring starts to elongate, there will be a spring force that will act along the spring in the opposite direction to the extension or the compression, right? And this is the spring force that we are talking about. So spring force can be written as negative times of displacement, right? And it is also quite logical. If you keep on elongating a spring, the greater the x is, the large amount of spring force you actually experience, right? And why negative direction? Because if this is the direction of displacement, then in the opposite direction to that the spring force will act, and K can be called as spring constant. Done? So now this is very important. Why? Because I mean, usually what we are going to do is we are going to use spring force in many ways. We are going to spring force in work per energy. We are going to actually derive what types of what is the potential energy stored in the spring. Then we are going to talk about springs in collision as well, right? When a block gets collided with a spring mass system, we are going to talk about it in conservation of energy. So this is a very important concept, right? In today's class we are just taking a glance over it, right? We are going to talk about spring mass system in detail in work per energy and in center of mass. Other than this, we can actually talk about one or two questions when the spring is in the steady state. What do you mean by steady state? A question something like this. Let's suppose that we have to find out the acceleration of this system, and we have got a block, 2 kg block over here, 3 kg block over here, and it is very important to note that whenever a question something like this comes, this is actually in steady state. Steady state basically means that the tension all along the spring becomes constant, and also there is no motion of this 3 kg block after this. That means it is at its maximum extension. It is not extending after this, right? It is at its maximum extension. Now see what's going to happen. If we are going to talk about this 3 kg block, I'm going to draw the free body diagram for you. You solve it by yourself. I'm going to draw 3 kg block something like this. This is 30 Newton. I've got a spring force over here, Fs. Similar spring force would be drawn something like this, right? A tension T and 1 kg block over here. That's it, right? Hopefully everything is clear. Now take a minute, solve it, unpause the video and check it. So let's apply the same logic over here as well. So for a 3 kg block, let's say the entire system is moving down with an acceleration A. So we are going to write 30 Newton minus friction force, minus spring force equals to 3 times of A. For 2 kg, we are going to write T minus Fs, and by the way, we are going to write actually Fs minus Ts. Fs minus T equals to 2 into A, and for the first one we are going to simply write T equals to 1A. So now it's up to you, solve it down. I have written the 3 equations for you. Find out what's the correct answer for this one. Alright, moving to the next one. Now let's talk about something that is known as pseudo force. Many students have problem over here because they actually worry about it a lot, that what is pseudo force, what are centrifugal forces, what are centripetal. You must not have any problem with centripetal, but what is pseudo force, what are centrifugal force, all of these kinds of things, right? See, first of all, it is a fictitious force that we use in those questions, in those scenarios where we have to deal with non-inertial frame of references and we have to apply Newton's laws of motion, right? So that's why sometimes it is the correct definition that it is a corrective force. It's a correction force which is used to explain the motion of objects in the non-inertial frame. A very easy thing to understand. Let's suppose that you have got a body, you have got a car and it is accelerating with an acceleration A, and over here you have got a metallic bob tied from roof of this car, something like this, of mass m, right? So now you have got like 2 frame of references. One frame of reference is of the ground. Now for this frame of reference you don't have any problem. So first of all, before writing the equations of motion, please understand about which frame of reference you are writing it, right? If the frame of reference is ground, you don't have any problem. This mass m is accelerating with acceleration A because it is inside the car and car is moving with an acceleration A. But if let's suppose you are inside the car and you want to explain that what is the motion of this block, then what you will have to do is you will have to actually apply a pseudo force, and that pseudo force will be in the opposite direction to the motion, written with the mass of the body times the acceleration of the object, right? That's how you are going to actually write pseudo force. Very easy thing, that's it, nothing to worry about. It only comes into existence when we are talking about non-inertial frame. Let's take an example. What horizontal acceleration should be provided to the wedge so that the block of mass m kept on wedge remains at rest with respect to the wedge? All right, with respect to the wedge, we are not talking about with respect to the ground. So if we are saying, let's suppose the wedge is moving with an acceleration A. So with respect to the wedge, we are going to draw a pseudo force something like this. Let's say this is MA, right? Mass of this block is mg. Sliding component of weight is mg sine theta. This force is mg cos theta, which basically means that this angle is theta. So this angle is going to be 90 minus theta. So the component of MA along the inclined surface is going to be MA cos theta. So if you want the block does not slide, this force must be equals to this force. right? So MA cos theta must be equals to mg sin theta. So we can cancel out the m. So A will be equals to g tan theta. So g tan theta is the correct answer, right? So hopefully you have got it how we are going to solve problems. Oh, definitely we are going to also do, see, this part of the Newton laws of motion will be a little short. Why? Because we are dealing circular motion after work per energy. So I am not going to talk about circular motion in this chapter. This is very important to understand, right? Why I am not doing that? Because I really want that before learning circular motion, let's complete work power energy. Let's talk about everything about the dynamics portion. Then we will do circular motion, right? Because then we are going to also solve questions through conservation of energy. After this, let's solve some of the more questions. Let's suppose we have got a 50 kg person stands on a 25 kg platform. He pulls the rope which is attached to the platform via the frictionless pulley as shown in the figure. The platform moves upwards at a steady state if the force with which the person pulls the rope is. Okay, fine. So see, now the thing is, to solve questions something like this, sometimes students have a problem. I'll give you a short trick. What you do is, you draw a platform and draw the free body diagram using a platform. So you have got a platform, right? On the platform, how many forces are there? There is mass of platform and mass of person. So quickly write down those. So I have got 50g plus I have got 25g. One thing done. Now the man is actually pulling the rope down, right? It is pulling the rope downward. So there is a tension. So there is a tension T acting over here. Let me draw it something like this. There is a tension T over here. We have got a same rope. So there is a tension T something like this. And there is a tension T something like this. Right? So I've got 3 T's over here. So that means 3T, and because it is moving at a steady rate, there is no acceleration. So 3T will be equals to, this will be actually 750. So T would be equals to 750 divided by 3. The platform moves upwards at a steady state if the person the pulls rope is, and we have to actually find out the acceleration. He pulls down. Okay, everything's clear. I think there is the platform moves upwards with a steady rate if the force with which the person pulls. Yeah, I think we have written each and everything over here. Let's see. Well, everything is clear. Tension comes out to be 250 Newton. I think there is a problem with the options. These options are not correct for these things, right? So the correct answer is 250 Newton. We have done no mistake, right? Hopefully everything is clear till now. One or two questions in homework. Solve this one in homework. Similar type of a problem. 60 kg painter is doing a similar kind of a thing, right? So slide number 30. Do it in homework. All right. Now let's move to a next topic, that is friction. Again, we have started a new topic under Newton laws of motion. So let's first define what do we really mean by friction. So friction is a type of a resistive force which acts to resist the tendency of relative motion, right? So it comes into existence to resist the tendency of relative motion. It acts between the surfaces to resist resist the tendency of relative motion. This is actually very important. Tendency of relative motion. Even if there is no relative motion but tendency of relative motion, right, then also friction force will act, and we'll talk about it using an example. What type of a force it is? Again, it is an electromagnetic force in nature. How does it act? It acts tangentially. It acts tangentially to surface, right? Now, let's discuss what do we really mean by tendency of relative motion. And you might have seen those illustrations, especially from the junior classes, that it is because of interlocking of what we can say of surfaces. That's not the correct depiction, that's not the correct representation how the friction force works. Friction force is much, it is more like the particles of the two surfaces, the intermolecular particles of the two surfaces, they form bonds with each other, right? They somehow weld into each other. Well, when I say weld, they actually form attractive bonds with each other. Attractive, they are attached to each other with an attractive force. To break that attraction, we need an external force, right? So quite easy things. Let's suppose we have got a rough surface over here. We have got a block kept on this surface, and we have got an external force acting on this block in this direction. Now, I really don't know what will happen because of this external force, but definitely there is a tendency of relative motion in this direction. That's what I was trying to say, that there is a tendency of relative motion in this direction, right? So, to resist that tendency, friction force will act on this block in this direction. And like all other forces in universe, friction force also acts in pairs, and they follow Newton's third law. By the way, we have not done right now Newton's third law. Newton's third law, which is actually every action has an equal and opposite reaction. So the another force will be drawn something like this, which will be on the ground. This is the friction force, and not let me right now not write it as, let me just say that this is just F, right? Now after this, we are going to say that, okay, now it actually depends whether the particle was initially whether the body was initially moving or whether it was at rest. Because when we are going to talk about friction, there are going to be mainly two types of friction. One is static friction, and the another one is kinetic friction. Right? So, to know more information about the surfaces, we also have got coefficients of friction. So, like for example, if we are talking about static friction, we have got coefficient of static friction. If we have got kinetic friction, we have got coefficient of kinetic friction. And mu s is always greater than mu k. Why is that? Because I mean, obviously, if we have got two surfaces which are at rest to each, which are at rest with respect to each other, maximum number of particles are in contact with each other. So the force that we were talking about is actually now it is acting at with the greater extent, right? So to break that attractive force and to make those bodies move with respect to each other, we need a larger force to overcome static friction, and that's why the value of static friction is greater than the kinetic friction, right? Moving on, let's talk more about static friction. When we are going to discuss about static friction is actually a type of a self-adjusting force. It's a self-adjusting force or a self-adjusting friction. Why is that? So I'll give you an analogy. So this was ground, this was the another body, and these are the particles which are in contact with each other. And if an external force wants to move this object over this surface, it has to overcome the frictional force. Now let's suppose the maximum friction force that can act between these two surfaces is, let's say, 20 Newton for an instance, right? So in this case, let's suppose if you are going to apply an external force of 10 Newton, this is, let's say, this is an external force. So is there any requirement of friction force to be 20 Newton, or for that instance any value greater than 10 Newton? Of course not. Why? Because right now the tendency of making this body into relative motion is only because of this 10 Newton. So that's why in this particular case the friction force will also be just of 10 Newton. So that's why we are calling it as a self-adjusting friction. So definitely it has got a maximum value. So static friction is a self-adjusting friction. The maximum value is known as a limiting value of friction, and the minimum value can be 0. I mean, if there is no need for friction, static friction will not apply, right? Something like this. And that's why you have got graphs over here which talks about, let's say, you have got external force over here and you have got friction force. So the graph is something like this. And then this, so this is going to be the limiting value. This is the limiting value of friction, and after this it comes down, and this is the value of kinetic friction. So kinetic friction remains constant, right? And its value is slightly less than the value of limiting friction, right? So very important that understand that it's a self-adjusting force. It comes into existence according to the need. So if there is a need of kinetic friction, if there is a need of self-adjusting friction of a particular value, it will act. If there is no need, it's not like that always the maximum value will act, right? And the limiting value of friction is written as mu s into normal reaction. This is the formula for limiting value of friction. And for kinetic friction, the value is mu k times normal reaction. All right. And now you know how to write normal reaction because we have done all of those things. So now, as we have completed a little part of friction as well, now we can discuss what do we really mean by contact force. So contact force, it is the tangential component of the net contact force acting between the two bodies in contact. Now see, so let's suppose we have got a body kept over here which has a tendency to move in this direction because of some external force. Let's suppose because of some external force over here. And what are the different forces we have got? We have got mg over here. We have got normal reaction which we actually, if you remember, we said that normal reaction is nothing but a component of contact force. And we have got friction as well. So the resultant of these things will be drawn something like this, and you can call this as F, right? And this is going to be under root of n square plus F square. This is the contact force that we are talking about. All right, so hopefully everything is clear. Now you can play with this formula as much as you want. So the contact force right? And the minimum value of this force can be n when there is no friction, and the maximum value is this, right? So hopefully you have got it. After this, we have got one or two more concepts regarding regarding friction and regarding some angles. That is, one is angle of repose. So what happens with angle of repose is, let's suppose we have got a block and we want to know that if mass of this block is m, mass is constant, the coefficient of friction of this surface is mu. Keeping all of this constant, we want to know what should be the angle theta after which this block will slide down, right? So for that, let's draw all the other forces. I have to draw mg sine theta over here. That's what is required. Mg sine theta is required. And to resist this, friction force will act, because the tendency of sliding is down, right? So the friction force will act up, and the friction force will be mu mg cos theta. Why mu mg cos theta? Because now the normal reaction is mg cos theta. Here we have got mg cos theta, and this is the normal reaction. So the maximum angle would be when mu mg cos theta equals mg sine theta. So obviously we can cancel these things out. So tan theta is equals to mu, and theta comes out to be tan inverse mu. So you can also remember this thing. This is known as angle of repose. That is the maximum angle after which the block will actually slide. Right? So hopefully everything is clear, my friends, till here. Now, to make your concepts more clear, let's start with some good questions. So this is the first one. In this one, we have got, see, we have got three surfaces. One surface is between A and B, another surface is between B and ground, and between the surface between B and ground is smooth, and the surface between A and B has a coefficient of friction of 0.4. They are saying calculate the acceleration of the blocks and the force between them. Now there can be two conditions. The two conditions are, sorry, there can be two scenarios. The two scenarios are one, blocks move with same acceleration. Second, obviously different acceleration. These are the two scenarios. Now how to find it out, which is the case, right? So this is the way how we are going to start solving these problems. The first thing is, assume that they are moving with the common acceleration, right? So the first thing is going to be assuming that assuming and finding common acceleration. Alright my friends, so common acceleration is going to be the net force is 50 and the total what we can say total mass is actually of 15, right? So this is going to be 10 by 3 meter per second square. Alright. Now see, the force is acting only on 5 kg block, and if you want me to draw the free body diagrams of these things, I will draw it for you. For 5 kg block, my friends, there is a net force acting in this direction of 50 Newton. There is a friction force acting in this direction, which is of Fs, right? F, whatever you want to write it down. And if you want to write down the free body diagram on 10 kg, there is only a friction force acting in this direction. So let's forget about the 5 kg block. First, let's find out the acceleration needed to move 10 kg block with this value. So the force which is needed is 10 times 10 by 3, that is 100 by 3, which is near around 33.33 Newton. Is that correct? Right? So if this is the required force, so let's find out whether friction force is sufficiently large enough to, will it be able to provide this acceleration or not? So the maximum value of friction is going to be mu mg, which is just 20 Newton. This means that friction force is less than the required force. So they will move with different acceleration. Please think about it. Pause the video. Don't move forward if you're not getting it. It is quite easy. It is the job of the friction force to make them move move together, right? That's what the friction force does. That's why it actually comes into existence. It does not want that the two surfaces actually slides over each other. So the maximum friction force can act as 20 Newton, right? And the friction force that we need to move this block with the common acceleration is of 10 by 3 is actually 33.33. So they will move with different acceleration, and how to find it out? So this 10 kg block will actually, now the maximum friction force will act 20 Newton. 20 Newton divided by mass 10. So this is the acceleration of 10 kg block. So this is 2 meter per second square. That's it, right? So this is 2 meter per second square, and find it out for the 5 kg block. This is not the correct answer. For 5 kg block, the force in the forward direction is 50 minus friction force in the backward direction is of 20 divided by the mass is of 5, that is of 6. So 6 and 2, that is option 2. Hopefully you have got it, right? So now after this, I've got one more problem for you, and this is something like this, right? Again, let's read it. Figure shows two blocks tied by a string. A variable force F equals to 5 T is applied on the block, and the coefficient of friction for the blocks are 0.6 and 0.5 respectively. Find the friction force between the block and the ground as well as tension in the spring at 2 seconds. All right, please just let's quickly do it. If force is of 10 Newton, right, because they are asking at 2 seconds. So if this is 10 Newton, let's find it out. What is the maximum value of friction that can act over here? So maximum value can be 0.5 times 20, that is 10 Newton, right? So it is exactly equals to 10 Newton. So it will not move. So if it will not move, anything will not move, right? So actually, if A will be actually if A will be 10 Newton, FB will be 0 and tension will be 0. So its option is A. I know it was quite easy, but what I'm going to now do is please find out for t equals to 3 seconds. Then things will change. Why? Because see, maximum value is 10. If this is going to be 15 Newton, then this can act only up to 10 Newton. Then the net force is in this direction, which is of 5 Newton. Then find it out using the same options, right? So that will be all, my friends. Don't forget that most of the other things that we have skipped in today's class will be dealt in circular motion and work power energy, right? So thank you so much. Please stay connected, and I'm going to come up with now the next topic is going to be work power energy, and along with that we are going to also do circular motion, right? So going to meet you same time, same day next week. Thank you so much. Bye bye. Take care.